Yeah, so let's start with the main theme of today's lesson. So we are going to talk about deep learning, but what is deep learning? Basically, given some input data, you have some algorithm which produces some output which approximates your desired function f. So you have like a mapping f, which given x returns some y, and your deep neural network also given x should return something as close as possible to y. And examples of deep learning applications, probably you have heard about many of them, but they can include, for example, object detection. You have a picture of a dog and a cat, and you want to put a rectangle on a dog, put a rectangle on a cat, and detect where they are located in the image. This is especially helpful in autonomous driving, for example. You have translation from English to French, from any other language, speech to text, which generates text transcription given an audio. There is a vice versa task where you have a text and you generate audio, image generation. Deep neural network can play chess for you or any other game. And there is some hard, complicated biology stuff that I don't understand, but probably someone of you can understand what is going on here. But one of the most important things you need to understand from this bootcamp is that you should think about tasks, not about the specific domain of your work. What do I mean? For example, you want to do a classification task. You have a dog, you have a cat, and you have a picture of a dog or a cat, and you want to understand whether this is a dog or a cat. But this is exactly the same as having one plant and another plant and try to detect what disease this plant has. Or maybe you have several texts. One is about IT, another about sports, and you want to understand what is the topic, sports, IT, news, something else. So without any examples, this will look exactly the same. Given some input data, your model returns one of n classes and nothing harder than that. So if you want to do classification for audio, you don't need specifically to go and listen to audio. You can still listen to how classificate cat and dogs, and after that you will be able to classificate audios, and the pipeline will be basically the same. Or, for example, you have a music piece and you want to produce the second bar for this music piece. Or you have like a series of a time series for like from 0 to point n, and you want to predict what is going afterwards. So it is called time series forecasting. Or your favorite LLMs like ChatGPT, Gemini, Llama, all this stuff, they all these three examples, they work exactly the same, and it is called after regressive modeling. Given some sequence from 0 to n minus 1, you want to predict the next element of this sequence. Or generation. If you want to generate pictures or you want to generate audio, with diffusion, you do it from some random noise. And the idea is exactly the same for both of the domains. Given some noise, your model returns some output using the same algorithm. The only thing that changes is like the type of input for us as humans. For the model, it will be just some metrics and it doesn't care. So the general concepts are identical for different domains. And if you know something about one domain, you can easily apply it in another domain. You don't need to specifically listen to the course about deep learning for biology. If you want to do deep learning for biology, you listen to some general deep learning course, and now you are able to apply the same stuff in biology, for example. And there is one cheat code for maybe PhD students, if there are any here. You can read some publications about, for example, computer vision. Take this new idea from computer vision, say, okay, I will apply it in audio or in text. you just apply the same idea with minor changes, and you get a new publication in audio or in text, which is accepted to top conference, because that's how deep learning practical papers work. So yeah, you can just transfer concepts from one domain to another, incorporating new domain-specific knowledge, or just taking it as is. Okay, questions? No. So let's move on with what is deep neural networks. Yeah, given X, your deep neural network returns the X, some output. It can be like binary, it can be discrete, it can be continuous, depending on how you define the output for deep neural network. And it tries to approximate some Y. You start with some random prediction, and the process of changing your deep neural network in a such way that this prediction gets better for over some number of this after some time of you changing this model is called training. Yeah, one remark before we move further is you probably heard about the term machine learning. You heard about deep learning. What is the difference? So the difference is in algorithms. The pipeline is very similar. Like given some data, you do this training, and given some data, you do some inference. But for deep learning, when somebody says deep learning, it is mostly about neural networks, which can be seen as a computational graph. We'll look at it on the next slide. And deep neural networks can extract meaningful features on their own without any human modifying the input in some fancy manner. Like you can take the raw image without any modifications, and your neural network can do pretty well just on this image without any modifications. But with machine learning, this won't work. With machine learning, your features must be handcrafted. Machine learning cannot work properly on some complicated data without you extracting some features before passing this to machine learning algorithm. So when somebody says machine learning, they mean one of the simple algorithms like linear or logistic regression, decision trees, boosting, random forest, SVM, Gaussian mixture models, etc. So the general thing about machine learning, these are some relatively simple algorithms which are relatively easy to interpret, to understand how they work and why they work, and that require some handcrafted features to perform well. For deep learning, one important remark also is that it can do well from raw input without any modifications, but sometimes adding some handcrafted features also helps deep learning models to do better predictions. Questions? No. Okay. So what about training? Training deep neural networks is an iterative process. So given the total number of iterations, you do 3 steps each iteration. First, you get some data to train on. It's like a pair of examples like X and Y. Then you do so-called forward step or inference of your model. Given your model, you predict this output Y, and also predict a thing called loss. We'll talk about it later. And then, given this loss and your model, you update your model, changing its parameters in such way that this approximation, this deep neural network becomes better. So let's look at one iteration. You have input data, you have your model, and your model returns some model output. And you have your desired output, this Y. Given your model output and desired output, you can calculate some measure of similarity between them. For example, you want your model to generate dogs, but it generates cats, so you will have like a high loss saying that cat is not similar to a dog. But if your model predicts something which is relatively look like a dog, this loss will be smaller, and you want to penalize your model for giving wrong predictions, and over time this loss should become smaller and smaller. So your model should predict better and better. And calculating model output and this loss is called the forward step. During backward step, you take your loss and you calculate gradients. We'll talk about how we can calculate gradients, but given these gradients, you can pass them to your model and update its weights. And you will have updated model which should perform better. Let's talk about each of the steps individually to understand better what is going on. So the first thing we need is data. And this is about a data set, which you use to train or evaluate your model. If the data set contains some ground truth examples, so this Y, the task is called supervised learning, because you have an exact example of what should be predicted. We won't talk about unsupervised, semi-supervised, self-supervised, and other topics during the bootcamp. Probably, yeah. We might talk about self-supervised, but on the second week. So for now, always when I say data set, let's assume that we have input and the desired output, which is this ground truth prediction. It is very important to split your data into several partitions. So you have like full data set, many examples, and you split it into some partition which you train on and some partition which you evaluate your model on. Why? First of all, when you have an example, when you have a data set, this is some limited number of examples your model can see. Yes, it can be large, but it's not all possible examples in the world, because all possible examples are like continuous infinite number of these examples. You see just some finite number of elements. So probably your data set looks like something on the left, or it could look like something on the right, and you do not know which of these examples you have, and you cannot have like all these possible examples. You cannot have all orange dots here, 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 and here. So this is the first issue. And maybe you train your model on this data, but you won't know how it will perform on somewhere here, because you have no examples here in your training data. But if you use this as a training set and this is a test set, you could look at this point and understand that your prediction probably is not very good. The second thing is that your data usually is not clean, it is noisy. For example, your task is to predict some stocks, some money, and maybe the real money is like, I don't know, $300, but because of some noise during calculations, you get a data set with 301, something like this. And in reality, your points won't be directly on this. I forgot to say this. So this gray line on the plot is your function you want to approximate. So this is like the correct answer, and orange dots are the elements you see and the elements you observe. And the issue is that, as you see, some orange points, they do not lie on this gray line, because you have some noise in your data. So you imagine you have only one split without any testing. You have only a data set to train on. then probably your model would look like this line on the left. And you see that it's definitely a bad predictor because your ground truth function looks nothing like this curve here. Or probably your model trained to be something like a picture on the right. And you see that you can almost perfectly fit your training data. So your model is a good approximation of these orange points. But here, the orange line goes almost to infinity, while the gray line definitely is not like that. And you, without any test data, you have no ability to verify if you have such a problem or not. So also there is such thing as underfitting and overfitting mentioned here. So underfitting is when if you change like one of the elements in your data set, your prediction will change significantly because it's a very bad and not robust approximator. And overfitting is when you approximate training data so well that you also learn some noise, which you should not learn. And you perform extremely well on training data, but if your function looks nothing like a ground truth curve that you wanted to predict. Yes. So splits are required to answer the question how good your model actually performs. You cannot use training data to answer this question because your model was trained on this data, so it knows for each element X in the training data, your model already knows what is the desired output Y. And this cannot be used for verification of your model. So performance assessment should be done on some unseen data, and this is your test split. Yeah, so if you have this training data, orange one, and a new test data, which is a green one, you could easily see that your model overfitted and its quality on unseen data is actually bad. And as a predictor, your model is actually also bad because you have this huge difference here. And maybe you train some another model, the black one. It is not as good on these orange points as you see, but it is much better on these green points. And it looks much more like your original gray curve. So with this test data, you'll be able to find a better approximator, not just something that learns training data. Okay. What do you have here? Sorry. What is this? Oh. Yeah. So one remark, in practice, you usually want to have 3 splits. One is train, one is test, as we saw, also known as evaluation test set. And the third one, a new one, is called validation set or development set. So the thing is that when you train a model, you usually have some things you want to modify, some hyperparameters, so-called hyperparameters. And if you modify it a better quality on the test data, you won't know how your model will perform in real life because you are changing your model to get better prediction on some data you already have. So it will be the same problem as for training split. You adjust something for a specific data set and you won't know how your model really performs. With the validation set, you are allowed to modify some hyperparameters. So you will assess the quality of your model on this validation set, change some hyperparameters, and then with your best model on this validation set, you can finally evaluate it on the test set to understand how your model performs in the wild. A good example, you are a company worker, you have some model, you trained it on some data set, and now you are putting it in production. And in production, you can't change your model anymore. Yeah, so if your model performs bad on real users, it will be a disaster. And using some unseen data, you want to evaluate like have some kind of measurement on these unseen users that will actually use your model. Okay? Questions? No. Yeah. So because the data is unseen, the performance may be much worse than on the training data, because training data is only a part of all possible examples, yes, and on the seen data, it can be significantly different from this training data. So to mitigate this problem, there are several generalization techniques, and one of them is called data augmentation. So you have your training data and you want to transform it slightly so the output, the ground truth output is still the same, but the input is slightly different. For example, you have a picture of a dog. If I erase the face of a dog, you as humans still know that this is a dog because like it looks like a dog. So you want your model to also know that this is a dog, even if you see only this part of a dog. Or if you zoom in to the center of a dog, to its mouth, you still, as human, know that this is a dog. And with all other modifications here, you as human also know that this is a dog. So the goal is that your model should also be robust to such modifications, and your model will learn what actually in a dog make it look like a dog, and not just how your training data is distributed. And this will hopefully increase your performance on the test data. Questions? No.
Yes, so the data augmentation is done on the training or?
On the training data. There is one remark here. So probably you may want to do some pre-processing for all your input. For example, you always work on grayscale images, not on color images, but on grayscale or black and white images. So then you will have like an augmentation like this, but you will apply it both on the training set and on the test set, because you want your model always to look like, to always be in a grayscale. Or maybe you always want to take only the central part of your image because you want to work with some small part of the model. Or for example, you do like Face ID, like on your iPhone or Android phone, it looks at your face, yes. But if I like imagine like this is a phone, I can look at it like this, yes, and I can look at it like this. And for my phone, my face can be like in the left part of the image and on the right part of the image. Instead of working with all these cases, at first I pre-process my data, my input for the phone to get a crop of my face, and the model will always see just the central face, just the central image. It won't have me on the left or me on the right. It won't have. Okay. And in such case, we will do this on both training data and test data and any data. Yeah. So this won't be like an augmentation. It will be called like a transformation or pre-processing. Questions? No. Yeah. So we talked about models, but what is actually a model? So in a simple way, deep neural network can be seen just as a computational graph. Some stack of layers that returns output given the outputs of previous layers. Here's an example with 4 layers. You have some input data. Your layer 1 takes this input data and returns something. Layer 2 takes this output from layer 1 and also returns something. And layer 3 does the same thing, layer 4 does the same thing, but it is possible that your layer uses outputs from many previous layers. For example, layer 4 uses output from the layer 3 and from the layer 2. And layer 4 produces your final output that will be an approximation of your function f. And computational flow can be as you want. So if you want, your model can return 2 outputs. And you can process them independently, like one branch processes one output, another branch processes other outputs, and then you combine them somehow in the final layer before you have your final output. Or maybe your whole model can have many outputs. So when you work with deep neural networks, you, like a kid, just take some blocks and you combine them with errors and nothing harder than that. Okay? So one layer is some function that uses previous layer outputs and or input data to calculate new output, which is either an intermediate output or the final output. Very simple. Okay. And with this computational flow, we basically do this forward step, which is taking the data, predicting some output. Now we want to understand what is a backward step and what is updating the model. And this part can be slightly, what is this thing? Yeah, sorry. So, and this part can be mathematically complicated a bit, but I hope to make it simple for you, given a simple example. Any questions before we go to the backward step? No. So, all your layers, they have some parameters. For example, your layer can be just taking a cosine of some parameter and multiplying it by your input data, like x1 multiplied by cosinus of some parameter theta. So what your model actually does, it wants to adjust this parameter theta to make a better prediction. So all your layers have some parameters, and backward step updates these parameters. That's what's going. And your goal is to find good parameters that allow predicting the desired outputs for some new inputs. Let's have this example on the right. You have a data set with points in 2 dimensions. Feature 1 and feature 2 are x1 and x2. And you have 2 classes, blue and red one. And you have some unseen data, which is this like black point here, black point here, and black point here. And your model is this slashed line here. And you want to adjust this line in a perfect, in the best possible way to ensure that, like, on the left part or on the top part, from the one side of your line, there is a positive class. From the other side, there is like a negative class. So like a red class and blue class. So yeah, this line can be defined by parameter theta and parameter b. And your deep neural network example will look like this, like x cosinus theta plus x2 sinus theta plus b. And your hyperparameters or just parameters are theta and b, and x1 and x2 are the input which you want to classify. So because your ground truth is binary, and if you look at this model, it predicts something which is continuous, you want to somehow get binary prediction from your model. How can you do it? For example, you can say that if the output of your model is greater than 0.5, then you say that your prediction is class number 1, and otherwise that it is 0. And to measure the quality of your model, you calculate some metrics which are different from the loss function. So what is the difference? Metrics are used to access the quality of your model in some human understandable way, and there are no restrictions on them. They can be non-differentiable. But loss function, because you want to do optimization using gradients, as we discussed, should be differentiable. And your metrics and your loss function can be completely different. Also, it doesn't mean that if you get better loss, it doesn't necessarily mean that you will get better metrics. There is some, so if you have a good loss function, given large enough number of iterations, you'll also get good metrics. But if the loss of one model is better than the loss of another model, it doesn't mean that this second model performs better or worse than the first one. So usually during training, we calculate these loss functions, but to evaluate our model, we calculate these metrics. And for classification, one example is accuracy. How many predictions we got right, we got correctly. So for binary classification, it will be like this. And loss function is just some measure of similarity L between prediction and ground truth output. And for classification, it will be it can be defined like this. It is called mean squared error. So you take the difference between the output of your model and the ground truth and calculate it, take a square of it and calculate the mean. Then you calculate the gradient with respect to each of your hyperparameters of your model, which were your theta and b in our example. And then you update your hyperparameters in a such way, which is called gradient descent. So you take your old values of theta and b, and you subtract gradient multiplied by some parameter theta, which is called learning rate. Yeah, probably said one thing wrong. So remember I said the word hyperparameter. So forget everything I said about the word hyperparameter before, and previously all hyperparameters were the actual parameters, and let me formulate it better. So if your parameter changes when you want to update your model with this gradient stuff, it is called just a parameter. Hyperparameter is something you predefine before training your model and what you do not change. It doesn't depend on the gradient, it doesn't depend on your loss function. You can modify it, but it won't depend on any losses, on the measure of similarity, etc. Okay, it can in some cases. Assume that it won't or cannot be changed. Like this learning rate is a hyperparameter. And before your training, you say, okay, my learning rate is equal to 1. And let's always use 1. As we'll see later, it's actually better to change it over time. and there are different rules how to change this learning rate, but this change won't be won't be based on these gradients. It won't be based on it won't be based on the parameters of your model. It will be based on the number of iterations or the quality of your model. There are other hyperparameters we will discuss, and I will say that, okay, this is a hyperparameter that we don't change, so you will understand what is the difference. Sorry for making a mess here. Yeah, so why we do minus here? So if you had calculus classes, you probably remember that gradient is a thing that says how to maximize, like the direction on how to change your parameters to maximize the output. But with loss, we want to get elements as similar as possible. So we actually want to minimize the loss function. So instead of going into the maximum direction, we go in the opposite one. And this is a negative gradient here. That's why we have a minus. Okay. And the step size, like how much we go in this direction, depends on this learning rate data here. Yeah, let's look at some visualization. So you have 3 plots here, and this is the data set we discussed with many points and 2 classes. And this line that splits your plot into blue and shaded blue and red parts is your model. Yeah, on the one side it is one class, on the other side it's another class. And your goal is to change this model in such way that red points will be in red shaded part and blue points will be in blue shaded part. So yeah, so we had this plot on the right, which is about our data. Plot below it shows your loss on each iteration. So you have your training loss. You want to minimize it because the smaller it is, the closer are your predictions and the ground truth. And over time, you want this loss to go down as much as possible. And on the left, there is your parameters theta and b, and for each point on this plot you have like a different color which also says the value of your loss. So the yellow color means that the loss is high, the dark blue color means that the loss is small. And you start at this white point here, and the red arrow will show where you are going on the next iteration. So how your parameters change on each iteration. And these black lines are called levels. They show where the loss is of the same value. So if you look at this like oval here, ellipse here, all points on this line will have exactly the same value of loss. So let's play. And as you see, with this gradient descent, gradient optimization, we go into this dark blue region where the loss is smaller, and also our classification got much better. Yeah, so we started at some definitely bad prediction, and over time, we achieved a prediction which is almost perfect. And we see that our loss went down. It's not exactly 0, but it got much smaller. So yeah. now that we understood gradient descent, in practice, when you have large models, you actually do not want to do it because, and when you have not large models, but large data sets, because your data set may contain like, I don't know, 2 million examples. And if you will try to calculate predictions for all 2 million examples, your hardware will die. You won't have enough computer memory, computational power, etc., to calculate everything. So in practice, usually you take a subset of your data, which we call batch, of a specific size B. This specific size, for example, like 64, 32, as like all computer scientists, we love to use 2 to the power of something, so it will be like 16, 32, but it doesn't matter. You can take any number of you want, like 15. So this batch size is a hyperparameter, and you won't change it over time. It will stay the same. So when you calculate your loss and gradient descent using only a subset of data, this batch, it is called stochastic gradient descent. Why it's called stochastic? Because each iteration, you take a new subset of data randomly. So instead of calculating loss on your whole data, you calculate it on this batch, and the equation is exactly the same as previously. But instead of D, you have this batch B here. And you calculate gradient for this mini batch like this. And you use it to update your model as before, like theta B minus learning rate multiplied by this gradient. So you save computation instead of D number of the size of D number of calculations. You compute only value for the B points, and B is much smaller than D, so it is much faster and cheaper. But mini batch is a noisy estimate of the full gradient. So there is some noisiness because you take only the subset, and the direction of your subset gradient probably will differ than the real gradient. But the goal is that if you take many iterations over time, your stochastic gradient will go to the position similar to the normal gradient. So like, imagine you like your stochastic gradient goes up, down, up, down, but on average, like it's here. And your full gradient, if it was here, yeah, so it will be the same thing. Let me turn off the sound. Yeah, so the same visualization, but here on the right, in orange, it is a full gradient descent, and in blue, it is a mini batch gradient. So on this subset of data. And for the subset, we take these points in black here. And as you see, the overall, the loss on your full gradient, the loss on your full data set over time goes down, but on your batch, it can go up, it can go down, it can go up, it can go down, because this is a stochastic thing. Like what is optimal for a subset doesn't necessarily mean that it will be optimal for the full data set. And closer to the end, you will still get very nice prediction, quality, decision boundary. But as you see, your loss is very noisy, your mini batch loss. And closer to the optimal, you will go in many random directions, but at the end, you will be at the optimal position or very close to it as you desired. Okay? Yeah. So let's do forward and backward pass for this example model to finally understand everything. we look at this model as a computational graph, as I say. So we have our theta, we have B, we have our x1 and x2. And our operations which we do are defined in these blocks, like we take cosine of theta multiplied by x1, sinus of theta multiplied by x2, we sum these outputs, etc. So when we do forward pass, we just follow these blue lines. Nothing hard. Yeah. Yeah, so we calculate Z1, Z2, Z3, Z4, etc. And finally, we calculate this loss, which is the output minus y and c square of it. Now we want to calculate gradients, and we do it with so-called backpropagation algorithm. And all nodes are differentiable. So you know how to calculate differential for cosine, for multiplication, for summation, etc. So what you can use a chain rule. Everybody knows what is chain rule. Yes, nice. So you start from the end, you calculate the gradient with respect to this Z9, which is taking a square, it will be like this. Then for Z8, which is minus, you use chain rule, you calculate the gradient via chain rule, and you can continue this until you get until you get gradient with respect to B and gradient with respect to theta. Okay. So if this was hard, then in PyTorch you still won't care because PyTorch does everything for you. So you only need to define forward pass, and PyTorch will do backward pass for you automatically. So you define your theta, you define your B, you have your X, your input data, your Y desired output, you calculate your loss as using this equation we said, how our model is defined. And in PyTorch, to calculate all these gradients, we just need to call loss.backward, and that's all. And we can get the gradients for theta and B using this dot-grad operation here. And we need to say requires grad equal true to say PyTorch that gradients for this element should be calculated, should be saved. Any questions? No. Okay. Yeah. So this learning rate, this thing which defines how you scale your gradient, like how big is your step, is called learning rate. And some people use a constant one, which doesn't change over time. It's like always stays the same. For sometimes it can still work, and you can achieve pretty good results. But from the optimization point of view, it is always better to adjust this learning rate to ensure that you achieve the optimal point. First of all, that you can achieve it and go like very close to it. And secondly, that you can do this in a reasonable time and not wait for 100 years to do the thing we for this simple model, for example. Yeah. So let's have another example of a model that looks like this. It's like some absolute value of y, some absolute value of x minus 10, and some scaling factor. So the loss surface will look like something on the right. Yeah, again, color defines the loss value, and black lines define the levels, which is the points with the equal value of loss. And you start from this point here, and you want to go to this optimal position here. So if you use constant learning rate, which is low, like here, it's hard to say what was the exact value in this example, but like 1e minus 7, for example. Then over time, your loss will indeed go down, but it takes many points to actually optimize your parameters. Because, okay, in some reasonable time, you went from this point somewhere here, but on this x-axis, you are going very slowly to achieve this optimal point, which was located here. So it is good if you have some noisy data, but it makes very slow progress along directions which are flatter. Yeah, and on the loss curves plot, you have example for, so the one which looks noisy is one example of a low constant learning rate, and the average low constant learning rate is, as far as I remember, it was like you try different small learning rates and then calculate the average loss curve. So ignore average loss curve, just like look at the single one. The idea is that your loss goes down, but very slowly. If you use high learning rate, you make progress faster, so you can go to the low loss value very fast. But the problem will be that you will, when you get close to optima or somewhere earlier, you will just always jump from one position to another, and you won't have any ability to actually make your loss smaller. Yeah, if you go here, you will jump here, and you can go like back and forth. So it is very noisy, and towards the end, it is not possible to get rid of this noise, and you won't be able to achieve even better performance with this high constant learning rate. So good constant learning rate is something in between. It's allows you to make progress fast, and also there is no so much noise closer to the end, and you can actually achieve some reasonable performance. But the best thing to do is do some scheduling where you start from some high learning rate and you end at some very small learning rate. This allows you to make progress fast at the beginning, but closer to the end where you are close to optimal, you can avoid these jumps by adjusting learning rate and allowing your model to do like smaller changes. So you can slowly get to this optimal position. And one of these schedulers is called cosine decay scheduler, which looks like a cosine. It starts from this cosine peak, and using cosine-like equation, the learning rate goes down to 0 over time. And with such a schedule, you get like the best of both worlds. You are able to go fast and get rid of the noise. There are many other different schedulers, but we recommend to use this one as like if there are many others, but if you don't understand the difference, or you don't want to understand the difference, or like you have a better thing to think about rather than choosing the scheduler, just use this one. This probably will work very good at your situation. Yeah, in practice, we talked about gradient descent and stochastic gradient descent, but in practice, people usually use so-called Adam algorithm or Adam W, which is a similar thing, and it just adds a few extra tricks to the calculation of your gradient. First trick is called momentum. So instead of using your gradient, you use your gradient plus some accumulation of gradients from the previous steps. So this allows you to reduce the impact of noise. This is far as I remember. And the impact of noisiness in this stochastic gradient descent, where you take a random batch all the time. And gradient normalization is this V thing. It will be used here. So you normalize your gradient so the changes are not too big. The weight decay, so this is a hard one. So usually when someone says weight decay and do some teaching, they say that weight decay is about regularization. And I also believe that this is true. But last summer, when Ali from machine learning optimization laboratory gave this lecture about optimization, he says that I'm completely wrong and almost everyone wrong, because it's just easier to interpret weight decay as regularization. But in real theory about optimization, weight decay is not a regularizer. It does something else, which is complicated. So we won't talk about what weight decay does. But having some weight decay usually helps your model to learn stuff more effectively. So the recommendation, like there are many different optimizers like SGD, ADAM, RMS prop, etc., etc. So again, as for schedulers, just use ADAM or ADAM-W. If you use weight decay, definitely use ADAM-W and not ADAM. And this would work for you most of the times. Yeah, and one extra thing that in practice, it is good thing to adjust your initial learning rate because depending on it, your optimization can get better or worse. You can take like not all the number of iterations, but some subset, like, I don't know, 1,000 iterations, and to see which initial learning rate helps you to get better quality, better loss for this subset of iterations. Because there is no magical value of a learning rate that is good for all the tasks. Like maybe for text-to-speech one, for your model, which you do for text-to-speech one, learning rate is better, but for another model which does also text-to-speech, but in some different manner, another learning rate will be more optimal, will allow you to achieve better performance or achieve this performance faster. So spending some time on turning your learning rate may be beneficial. There is a Twitter joke about 3e minus 4 always works. Like some random guy on Twitter said, okay, let's always use 3e minus 4. And for some reason, everybody hyped about it and started always using 3e minus 4. I would say that from my experience, 1e minus 3 or 1e minus 4 should always work. And if you do not want to change your parameters too much, you should use like 1e minus 5 or 1e minus 6. This is the case of fine-tuning, and I guess we will talk about this on Wednesday. So just recommendations that you should turn your learning rate. And another recommendation is that probably you should use a so-called learning rate warm-up, which means that you start also from some small learning rate, then you go to your peak position, and then you go down. Why this is needed? Because if at the beginning you start with a pretty big learning rate, maybe you jumped from some good initialization to some very bad random point, and then your model will try to get better from this bad position. But if you start with a small learning rate, you cannot go too bad too fast. So you like probably do some small adjustments, and probably you won't get into two bad positions, two bad locations, and you will be able to get a better performance overall. There is a question in the chat. How many steps for linear rate decay are needed in general? So for this cosine decay, the recommendation from Ali, from this machine learning, Atli, sorry, not Ali, Atli, from machine learning optimization laboratory was to use 5% of your iterations for warm up, and everything else will be used for the decay. Decay will be adjusted by PyTorch automatically. So PyTorch will know that, like, if you start this and you have a total like 1,000 iterations, it will automatically create a cosine schedule for you. So you don't need to think like how to make this curve. You just need to define the total number of steps. And if you want to use warm up, how much of these steps spent on the warm up. Yeah. So warm up can improve the quality of your model, and it won't hurt anyway. So usually it is a good thing to use it. Yeah. So yeah. So how to do this in PyTorch? So you have your model, you have your loss function, which is also called criterion. You can call it loss function, you could call it criterion as you want. So you define your model, you define your loss function, and then you need to define your optimizer. For your optimizer, you need to indicate what parameters to optimize. So this theta, this b. In PyTorch, you can just say model.parameters, and it will return all parameters for your model. And you need to say these hyperparameters like learning rate, weight decay, etc. Like these betas are for ADMW. Use the default ones. Yeah, like if you don't understand any hyperparameter, just use the default one. Is the only hyperparameters you probably want to think about for optimization are the learning rate and the weight decay. That's all. Yeah, from Atli also one recommendation was to use weight decay only for so for biases you should avoid using weight decay, and this is done by having this list here. So in Torch, it is possible to say that you want to use one hyperparameters for like one part of the model and other hyperparameters for another part of the model. To do so, you create a list, this bracket and this bracket here, and each element of this list is a dictionary. Dictionary with the key params defines the parameters of your model, and then you can add extra keys like weight decay or learning rate or etc., saying that for these parameters mentioned in this dictionary, I want to use this weight decay instead of the one defined here. Okay. I personally use this trick very rarely, so we will see how to do like a classic not too smart thing on Wednesday and probably today without these dictionaries. But just keep in mind that it is possible to give different hyperparameters for different parts of the model if you need this for some reason. And if you only indicate parameters and you do not indicate like weight decay or something, it will use the default ones defined here after this list. Okay. Yeah, and about this cosine scheduler with warm up, the thing is that in PyTorch there is no cosine scheduler with warm-up. There is cosine scheduler without warm-up, and there is so-called one-cycle learning rate. I thought that one-cycle learning rate is a cosine scheduler with warm-up, but again, Atli said that this is not true. And I usually use one cycle, but Atli's recommendation is that it is better to define cosine decay with warm-up, because one cycle has some worse optimization properties. So to define your scheduler, you call torch.optim.scheduler, and you pass your optimizer, and then you, in this lambda LR example, which allows you to do a custom learning rate, you just do this. And cosine decay with warm-up will be defined like this. Like before warm-up steps, you use a small learning rate, and then you do cosine annealing with this math.cosinus here. Here. And finally, the training loop we saw before, which consisted of three steps. Also here consists of basically 3 steps. You get your data, you calculate the output of your model and calculate the loss, passing the output of your model and the ground truth. You calculate gradients using loss.backward. You do optimizer.step to update your model. You call scheduler.step to update your learning rate. And you call optimizer.zeroGrad to delete the gradients from the memory. The problem with gradients in the memory is that if you avoid this line here, your gradients will accumulate each iteration. So your gradients of the second iteration will be the sum of gradients from the first iteration and the second one. And you, without, like, usually you want to avoid it if you don't know why you want to accumulate them. So people often forget about this line. Do not forget about it. So after each iteration, you want to delete the gradients from this iteration to avoid this accumulation. So this was all from the theory part. Yeah. Is it large enough for you? Yes. Good. Yeah. So we understood some theory. Now let's talk about some practice. And for this bootcamp, the practice is not like usually at EPFL where you have exercise session, you do everything on your own, and I'm just sitting and watching Telegram or something, yes, memes. So I think a better approach would be that we have some predefined notebooks and I go through it with you, explaining some stuff, explaining some code, maybe I will write some code with you, etc. So this will be more efficient, I believe. And you have access to these notebooks, so at home or anytime you can go through the notebook yourself if you didn't understand anything, etc. And also you can always ask questions on Discord where I or some other guy would answer your questions. Okay. Yeah. So we'll work with PyTorch. This is a framework for deep learning in Python, probably the most popular one currently. There are also TensorFlow and JAX, but people still mostly use PyTorch. So it is good to start with it, and it's also pretty easy. Yeah, what is a framework? Yeah, it's just some library that allows you to create, train, and inference deep neural networks, and also do some math and linear algebra operations. There are a lot of examples and tutorials. If you download this notebook, you can go through this link and see official tutorials from PyTorch and its community. There is there are some useful links for the PyTorch basics and how to train a classifier, but we will also go through it today on Wednesday. And I asked all other lecturers to prepare some notebooks for you for all the topics we're gonna have, like audio, CV, etc. For audio, we probably won't have one, but we'll see. Oh, we have keyword spot. Okay, well, hopefully we'll get some practical novels for all the topics we have. So we start as usual. We just import some stuff like Torch, NumPy, Matplotlib for visualizations, just some fancy trick for Jupyter notebooks and other fancy tricks to make Matplotlib visualizations look better with a better quality, and Seaborn just to get a grid for the images. It's probably for the plots, it's probably an overkill because you can call plt.grid, but we won't care. So when you work with PyTorch, you work with tensors. What is a tensor? Tensor is like a matrix, but with more than 2 dimensions. It can be like, no, with any number of dimensions. Yeah, it can be like, no. So theoretically, it's with more than 2 dimensions. But if you call 1-dimensional, 2-dimensional, like vector or matrix a tensor, nobody will kill you. So yeah, so tensor is just some element in with first dimension of size d1, second dimension of size d2, etc., dn. Here we use real values. It can be also complex values, but for simplicity, let's say that we always use real values. Yeah, and to create a tensor, you can use one of the two things. Either you have an existing array, like Python list or NumPy array, or you can use built-in functions like you do in NumPy. How many of you know NumPy? Like everyone, almost. You will get it like in 2 minutes, I think. So yeah, you have some iterable object like 1, 2, 3, and you create a tensor just by calling torch.tensor over this iterable object. And 1, 2, 3 list will look like something on the left, and tensor will contain the same elements, but it will be a torch tensor instead of just Python list. You can create the same thing using NumPy array. So in NumPy, you would call np.array to create an NumPy array using the same Python list. And to create torch tensor, we can again say torch.tensor iterable object. There is also torch.from NumPy. Maybe it is a bit faster than doing from doing it like this, but again, we do not care for now. And there are built-in methods. They're preferred because they increase speed, they increase the quality of your code in terms of like how easy to read it is and how well it's structured. And also they save memory because they do not directly, so they directly create a tensor instead of first using memory to do like an NumPy Python list and then convert it into torch.tensor. So, for example, if you want to create elements from 0 to 2, you, or from like 0 to n minus 1, you call torch.arrange n. In this example, it's 3. And this is exactly the same as in NumPy. It was np arrange, and we have torch arrange. So if you know NumPy, getting familiar with PyTorch will be very easy for you. For each tensor object, we can access some meta information. For example, what are the type of the elements, floating points, integers, complex numbers, bool, etc. We can also access the size, also known as shape, which is the size of each dimension. Like if you have a matrix 5 by 4, the size will be 5, 4. And also you can check the number of dimensions. We have one-dimensional vector, so number of dimensions which we got using tensor.dim is 1. Regarding the size, you call tensor.size, or you can use tensor.shape without brackets to access the shape of your tensor. Yeah, you can create multidimensional tensors, so with more than 1 or 2 dimensions. Here I use torch zeros to show that you can create a tensor full of zeros with a desired shape. Like this, we just pass the shape and we will get a tensor of shape 3 for the first dimension, 2 for the second dimension, and 5 for the last dimension. Or you can create a random tensor with elements from n01. Sorry, yeah.
Number of rows. How do you define 3 to 5?
So it will be the first dimension, like so like height, width, etc. is just like some things for us as humans, yeah. Like if you have a square, yeah, we say that this is height, this is width, and if you like care about the order,
Color is white.
Yeah, can you?
sorry. Yeah, so if you have like a matrix of height by width, and your question is, as far as I understand, basically about like the order, yeah, because if you say like shape is 2, 3, whether it is about the height or the width, yeah. So in this example, we the first 1 second. So it will be at first you choose the row, then you choose the column. It will be like this. So 2 will be the number of rows and 3 will be the number of columns. Okay, and if you have more dimension, like for example, it will be like the depth, and you put it here, it will go before height and width. Okay. But if you get lost, like you just create some example, like I want to have column 1, 2, 3, and another first row 1, 2, 3, another row maybe like 4, 5, 6. I didn't this. Yeah, so you can still verify it like this just by accessing the element of your tensor. So your tensor will be like this. And actually, by looking at the brackets, you can understand that if you at first you choose the row, and then you will choose these columns. And in order to access like the first row, you take square brackets, you say the index of the element of the first dimension, the first dimension index. Like for example, we want to take the first row, and in PyTorch the indexes start from 0, not from 1. Then probably we want, for example, to take the second column. So we will do like this. And it should return 2. Also, it is possible to do something like this, where we have 2 brackets instead of 1. I won't go for now, like when does it matter. So can we do like this? If you want to take a subset of columns, we, as in NumPy, use 2 dots and then like the range. Like we want to take from the first column to the second column. Yeah, so we have the first is included, the last one is not included. So in order to take the first and the second column, we will need to go from 1 to 3. Also, there is an alias. If you want to use like the last column, until the last column, you can use -1. It will be as like the last number. You do not need to explicitly write 3 here. Okay. Sorry for this noise. Yeah, so it is also possible to reshape tensors, and you have 2 methods for this. One is called view, another is called reshape. View and reshape does exactly the same thing, with my one minor change is that view just like when you call reshape, no, some background, like your objects in Python, they're stored in memory in some like blocks, and view doesn't change how these blocks lie in memory, while reshape will change the places of these boxes to ensure that like everything is calculated correctly. So you can always use view, but if for some reason PyTorch says that there is some error, you can change it to reshape. So reshape is a bit slower because it does this memory trick. And view works almost all the time. If it doesn't work, you will know about this from PyTorch. So use always view, and you'll change it to reshape only if there will be an error. So you have this tensor, and in this example, with elements from 0 to 9. And probably instead of having this one vector with 10 elements, we want to have a matrix 2 by 5. So what we do, we call tensor.reshape 2 by 5, or we can call tensor.view 2 by 5. And as you see, our tensor will be reshaped in this matrix format, not this vector. And notice that changing this view and reshape didn't change your original tensor, so it looks like it looked before. And it is also possible to do multidimensional reshapes, so we can, if you want, take a vector of size 100 and reshape it into tensor 2 by 5 by 10. Everything will work. Also, you may want to swap some dimensions or permute them. For example, you had this, like imagine this is my matrix, yeah, and I want it to look like this, yeah. So to do this, I can either call transpose with indication of the index of dimension which I want to swap. Yeah, so here I will like say swap -1, -2. So swap the height and the width, and it will go like from this to this. And yeah, if you look here, the shape was 2, 5, 10. After I transposed the last 2 dimensions, the new shape is 2, 10, 5. Okay. And it is also possible to change multiple dimensions in the order of them. So maybe from 2, 5, 10, you want to get 5, 10, 2. Then you call dot permute and say this permutation you want to use to change the order of your dimensions. When is it useful? So, for example, some models like recurrent neural networks, as we'll discuss, or transformer, they may require, if like the implementation works like this, to work always like with elements of such shape. No. So remember I said about the thing called batch size, yes, batch. So in practice, you'll have like an extra dimension which is for batches, and all your elements will look like this element here. So you have a batch dimension, and each element in the batch will look like this. So maybe for some reason your model want batch dimension to be the last one, or to be the second one, and to be like height here, batch here, and width here. It's just how the layer is implemented to be more efficient or parallel, etc. So sometimes you may want to do this permutation for this implementation purposes. Or maybe one of your libraries, when it's working with images, it wants the color channels to be like in the first dimension, some other wants to be, wants the color channels to be in the last dimension. That's why you want to do this permutation sometimes. Or another example, maybe your layer applies some function row-wise, so for each row independently. And you want at first apply this function on all rows and then on all columns. Instead of creating a new layer, you do permutation and you apply the same function on all rows now, but these rows now are what was columns before, okay? So the common operation is to add extra dimension, which is also called like in English, like invisible or mimic dimension. So this is a dimension of size 1. It does absolutely nothing except it adds a new dimension, and your shape goes from like 2.5 to 2.15, for example. To add such imaginary, it's called dimension, you call tensor.unsqueeze and the index of dimension where you want to add this imaginary dimension. When do you want to use this? For example, you work with images in grayscale. Grayscale have only one color, which is like black and white, and your tensor actually is like 1 by height by width. But for some reason, you saved your data as only height and width because you know that your channel is only one. You have only one channel. But your layer probably will require to know how many channels you have. So instead of working with height and width, you will need to manually add again this imaginary direction, the dimension for the color channel. Okay. Yeah, another way to do it is to call this dot none dot, which will say that in this place of none you add like another dimension, but it is harder to read, so always use this unsqueeze. Yeah, and there are many other operations. You can just go to PyTorch documentation. It is very good. And if you need some operation to do some fancy stuff, probably there is like an implementation for it. Or so just like always check like in NumPy or that probably there is an operation that does something for you, which is already built in. Yeah. So like in NumPy, you can do certain operations on tensors some of them are built in. For example, you calculate the sum, the maximum, and the mean just by writing .sum, .max, or .min. These aggregation functions has some arguments like dimension. Maybe you want to take average mean only over the first dimension and not over the all elements. And this will result in a matrix instead of one vector. So if you had a tensor of shape 10 by 100 by 1000, if you just calculate the mean, it will be the average of all the elements. But if you calculate the mean over dimension 0, it will result in 100 by 1000 elements where all elements are average over this. So like you take all this, let's say, like, so let's say this is channels, this is height, this is width. And like you have a 10 image with 10 color channels, and you want to get like only one color channel. What you can do is to take this average over all the channels to get like something with one channel, something like this. And you can take average over several dimensions like this with 0, 1 here. Also, there is an argument called KIMDIM, which says that, okay, we can calculate the average, but we do not want to get to delete these dimensions we had. We just want to have these imaginary dimensions for some reasons, again, some operations. So if you say keep dim equal true, instead of getting tensor of size 100, we'll get of 1, 101. Yeah, and there are some other operations like Frobenius norm or L2 norm or other norms. And we can also multiply matrices or tensors, this operation or this operation like in NumPy, or maybe this operation. And all of this would work. Any questions? Yeah.
Said that the dimension of 0 with set to 0 just above. Does that mean that the average is the
Here?
Yes.
Yeah, so dimension equals 0 means that take average over the first column. It says 0 because in PyTorch indexing starts from 0, not from 1. Okay. Yeah, so until now, it seems that why do we need PyTorch? Everything of this exists in NumPy, and why should we use Torch? And Torch, in a rude way, is like NumPy, but with automatic differentiation. So we can calculate these gradients automatically, and everything else is like NumPy. And another bonus is that we can use like special hardware, like GPUs, and etc. using Torch, and we cannot do this with NumPy. But that's like a second thing. The main thing is that we are able to do this automatic differentiation, which will allow us to easily define forward step for our models and automatically define the backward step. So usually you would do something like this. You say like, okay, we want a tensor and to calculate a gradient for this tensor. So we'll calculate this tensor and say requires grad equal true. Then we define some scalar function, whatever, and say that whatever applied on A returns some value, which here we say, okay, it is like called loss. To calculate gradient of loss with respect to our tensor A, we just say loss dot backward, and the gradient will be available in A dot grad automatically by PyTorch. Yeah, so important thing is that this whatever function should be a function which depends on at least one tensor which requires gradient, as we will discuss below, because otherwise PyTorch will die and say that, okay, I don't know for what I should calculate gradients, so there is nothing to calculate gradients for. So let's look at this example. We have x, we have y, some random vectors of size 4, and we want to calculate x multiplied by y plus 10 and calculate the sum over this. What should we do? We just call p dot backwards, and we get dp with respect to dx just by calling x dot grad, or here y dot grad. Okay. Why we do sum here, not just say z dot backwards. So as far as I remember, PyTorch will return an error if you calculate not for if you try to calculate backward for not an aggregated value. So yes, but when we calculate loss functions, we usually want to get a scalar. So in PyTorch training of models, you will usually have like something like sum here or mean, and you will get a scalar value and just call this dot backwards. Yeah, if for some reason you do not want to calculate gradient for some element, these reasons can be, for example, you want to save the output of your model, but you do not want to calculate gradients for it anymore, and this element to be present in the computational graph of your model. For example, your model predicts images, and you want to visualize this image. After you want to visualize this image and put it like to matplotlib or something like this, you do not need this model to be on GPU. You don't want this model to be to have this computational connection with your model. You just have like a new object. So you call this dot detach to detach your object from the computational graph. This will create a copy which backpropagation won't pass through. If you save your objects like in a list without detach, they will be still used for computational graph, and you will probably get out of memory error or something because you saved a lot of data, and for each of this data you'll have a computational graph. Computational graph requires some memory, so if you have like a lot of data with a lot of, for each of them you save computational graphs, you will get out of memory soon. So if you do not want to use tensor anymore for any calculations related to the model itself, just use detach. If you want to do it without copying, so directly on the tensor, you should call detach with this underscore. Okay. Yeah, and for example, here, when we created this y, we have the same example as before, but we say that y is equal x0 detach. And we will notice that we, let me show you like this. Yeah, because we call this detach, and we use detached variable here instead of y0, there won't be any gradient passed through y, and there won't be subsequently any gradient passed through to y0. So we won't have gradients for y0, we won't have gradients for y because of the detach. Okay. Yeah. Also note that we want to reset gradients of a specific variable. For training, we want to reset gradients for parameters. As I said, previously, if we do not do this, our gradients will be accumulated. For example, you have two functions. One is x squared, another is 1 over x. So at first you calculate your gradients for the first function, then you calculate your gradient for the second function using the same variable x. If you do not reset your gradient, your output will be 2x plus minus 1 divided by x squared. So the sum of the two gradients instead of the gradient of the first one. So after you calculated this and then do dot backward, your output will look like this if you didn't do detach. Question? No? Yeah, so let's look here. Yeah, so we have the example x, we have x squared, and we compute the gradient, it will be 2x. As we see here, it is 2x, yes? Then we have 1 over x. We want to calculate the gradient, but it actually becomes not 1 minus 1 divided by x squared. It becomes 2x plus, it becomes this minus 1 divided by x squared plus the gradient which was previously stored here. So the gradients were accumulated, and this is an issue. So what you actually want to do, you want to call grad.zero to zero the gradients. And in PyTorch example, when we had optimizer and optimizer.zero grad, what it actually does, it goes to all these parameters and sets these gradients to 0 to reset them. Yeah, also note that if you are not resetting the gradients, yeah, accumulation happens all the time. And after like 1 million iterations, you probably summed many values, and you can like overflow the integer values, the floating point values, like, or your gradient will be extra large. Yeah, and instead of like optimizing your function, you will jump to some random points and your training won't actually work. So if you see that your loss goes up or that your loss doesn't change much, there might be a common mistake that you forgot to zero the gradients. Yeah, about loss going up, I forgot to say this during the lecture, but one thing that can occur, like if you choose learning rate which is too big, as you remember this plot with high constant learning rate. So it is possible that if you take even larger learning rate, your loss can go up. And also, yeah, if your loss is going up, probably there might be an issue with learning rate too. Yeah, so one thing about PyTorch which is not straightforward is that gradients are calculated for all the variables using this chain rule, but at the end they are stored only for so-called leaf variables. What is a leaf variable? So you remember that you have like a computational graph. Yeah, you go from here to here to here, maybe here. So a leaf variable is a variable that has like errors only, not inside but outside, so only outside errors. So this is a leaf variable, this is a leaf variable, these are like intermediate variables. And the output is the output variable. It's not a leaf variable. Okay, so these are leaves because they have only edges like arrows outside, and this all they have some arrows inside, so they're not leaf variables. And what PyTorch does, it calculates and it stores gradients only for these leaf variables. Yeah, so for example, this x is a leaf variable, this y and p, they depend on x, so they are not leaf variables. And if you want to get their gradients, you will get none, and also a warning from PyTorch that you want to get a gradient from not a leaf variable. Yeah, in this example, it is similar. You just calculate the sum of x and y. X and y are leaf variables. You can check if it is a leaf or not by calling .isLeaf. And if you actually want to store the gradient for some intermediate thing, you need to call method which is called retaiNgrad, like this. retaiNgrad, and this would store the gradient for this intermediate variable, and you'll be able to access it. As shown here, we are now able to get this vgrad, which previously we couldn't get. Yeah, another important thing is that at least one of these leaf variables should require gradients by setting requires grad equal true. Why? Because if you do not want to calculate gradients for this, if you do not want to calculate gradients for this, why are you calling dot backward? Yeah, if you do not want to calculate gradients for anything. So this will return a runtime error because here I say that requires grad equal false for all leaf variables. If I set at least one of them to true, it will work. If I set both of them to false, but say retaiNgrad, which as we discussed requires says PyTorch to save intermediate gradient, it will still return a runtime error, but this time because W depends on some variables, leaf variables which do not require gradient. So PyTorch didn't know that it should think about gradients and didn't save them. So this causes an error. Yeah, and if we call this retaiNgrad, but say that one of the leaf variables is actually requires gradient, it still may not work because W depends on Z and not on X, and Z doesn't require gradient. So W will still get an error because it depends on the variable which doesn't require gradient. And if we say that X doesn't require gradient, but Z requires gradient, everything will work because we have at least one variable, leaf variable with gradient, and we have this intermediate thing which depends only on this leaf variable which requires gradient. Any questions here? No. Yeah, so that's about optimization and automatic differentiation in PyTorch. As we discussed, one thing that we will need for deep learning models is our data sets. So in PyTorch, we have two things for this. One is called data set, which is an ordered set of all the data that you have. So one object, one element of this data set is a pair of, yeah, let me. So you say that your data is an ordered set, meaning that like here it is element of data element number 1, etc. Data element number n, etc. So each of these data element is like a pair of x and y, like input and output, desired output, ground truth. Or maybe you want to return also something else, like some metadata, like, I don't know, path to the object, maybe something else. But the main thing is that this is like your input data plus your ground truth plus maybe something else. And if you want to get like object number I, you just say data set. Yeah. So you call data set square brackets I to get an element on the ith index. Yeah, so given the index y, we return xy from the data set. And the data loader is the thing which combines your data into batches. So this is like your whole data set of size D from the slides, lecture slides. And we actually want to work with batches, like some subset. Data loader says how to get a batch, a subset from your data. For training purposes, you want to get a random batch. So take a random index here, another random index here, another random index here. For evaluation purposes, usually you do not require this randomness because you do not care. Why for training you require randomness? First of all, you want to use a random subset all the time because it's beneficial for optimization. Secondly, you do not want your model to learn the order of your data. There was a joke in Kaggle. Do you know Kaggle? It's like machine learning competitions, and like competition where you have some data and you want to predict outputs as good as possible, and the winner like gets some money, etc. So there was one competition where the data was bad because you were able to predict good results just by looking at the position of this object in the data set. So the model didn't actually learn to some features about the data, like whether it was cat or dog, but it just learns that like if it's the first object return like dog, if it's the second object return cat, it's the third object return dog, etc. So it learns some features which are not actually about the object, but about the structure of your data set, and your structure of the data set can be biased for some reason. So that's why for training, you usually want to shuffle your data, or in other words, take random subsets. So to create a data set and data loader in PyTorch, you want to import data loader and data set classes from this sublibrary. And to create a data set, you need to create a nested class from this basic dataset PyTorch class. What do you need to do? You need to say like class your name of the data set, in brackets the data set from PyTorch. Then you need to define at least 3 methods. First one is initialization, which creates some variables for you that you'll probably need for some purposes. We'll have a better example next Wednesday. Get item says, given an index like I, what elements to return. So given an index I, return data I. That's basically what we are doing here. So in init, we saved our data set as a variable named data, and here we access is index element by saying self.data index. And also we need to define the length of our data set, which is here is the equivalent to the length of this self.data here. And for example, we say that, okay, our data set is 1000 examples of random vectors. Each random vector, so each example in our data set is a vector of size 10. So that's what we are doing here. And we create this data set just by passing this object for initialization. And if you want to get x10, so the 10th element of our data set, we just say simple data set 10, and this will return the 10th element of our data set. If you want to return like 11th, we'll say 11 here, and so on. Yeah, and the length of the data set is 1000 as we created here, so everything works correctly. So now we want to split our data set into batches. We need to call a data loader over this data set and also say what is the size of our batch, like 20. Also, there are some other arguments here, for example, like shuffle, which say whether we want to take random elements or just take like first batch, then second batch, etc. So if you say shuffle equal true, it will shuffle your data and take random elements. If you say false, it won't shuffle your data. Yeah, so you have this data loader here, and this is an iterable object. So you can iterate over it through, for example, for loop, and each iteration will get the ith batch, and each batch will be of batch size, and the second and after sizes will depend on your data. Here, yeah, I say that instead of for loop, we can use next iter, like another method to get the next batch from the data loader, but and also you can do the same using islice, but most of the time you won't use it. So it's just like a fancy example. Usually you will have something like this. Just you go in a for loop over your data loader, okay? Yeah, and one important thing here, so batch in our example here is a tensor X, because our data set here returns only one element. But if we say that, okay, I want to return X and also the ground truth like Y here, so the output will be two elements, X and Y, like this. And batch actually will be something like this. So it will be X and Y equal next. And if you just say batch equals this, we won't be able to call dot shape, because batch will be like a list of X and Y, a pair of list and Y, and not just a single element. But we'll carefully look at this next time too. Any questions? No. So the final thing before coding today will be about optimization. So as we said, we want to do forward step, calculate some loss, and do backward step. But we can do it for deep neural networks, but actually the same thing works for finding the local minimal of any function. For example, you have a square function like this. Its minimum is here at the red point, and you start from a random position, for example, from here, and you want to understand like how to change my X to go through this to this actually to this minimal value. So what we do here, we define this function f, and we start from some random solution. Here it is defined by some random integer. We say requires grad equal true, so we are able to calculate the gradients. Then we want to define an optimizer. To do so, we say torch.optim, then dot, and the name of the optimizer. It can be like Adam or Adam W or SGD, something like this, anything. Then in the first argument, you want to pass all the parameters you want to optimize. Here we have only one parameter, which is our current solution, which you want to optimize. So we pass a list with a single element, this current solution. We pass a list because Torch requires us to pass like all parameters in the list. And then we say that for learning rate, we'll use 1e minus 2. We say that the total number of iterations will be 200, for example. And for each iteration, what we do, we say, okay, let's calculate the value of our function at the current solution, function current solution, And we also use this as a loss because we want to get the minimum of our function. For neural networks, we will have here as like the model output, and then loss is equal like for deep neural networks, it will be something like this. Like loss function, model output, ground truth. Okay. But here, like our function and our loss are the same thing because we want to find the minimum of our function. We zero grad the gradients to avoid this accumulation problem, which we talked about. We calculate dog backward to get the gradient for the current solution. And optimizer.step will update our current solution using this backpropagation or using this gradient descent rules. And this is just some visualization stuff to show how our solution changes over time. So let's have a look. Yeah, we started from some random point here, and we are slowly but going closer to this red point here. Okay. You can see the impact of the learning rate if I choose it too large, like this one, for example. Didn't start from the like, let's say 10. Yeah, now we cannot even see the solution because it somewhere in the wrong place. And if you choose a too small one, like 1e minus 9, yeah, we will go down, but very slowly. So this is the impact of learning rate we talked about, that, yeah, we are going closer to the minima, but very, very slow because our learning rate is too small. So in this example, yeah, let me return to some like okay-ish learning rate. Yeah, we're slowly but getting better. It was like 1 minus 2, yes, as I remember. Yeah, so in this simple example, it basically shows you how PyTorch optimization of the deep neural network work. Everything will be exactly the same for deep neural networks, but instead of this simple function, you will have your DNN. So what you will do, you will define your model, you will create a data set and data loader to get your data and to get batches. Then you will define an optimizer like Adam or AddOW. And instead of passing this current solution, you will pass model.parameters to optimize model weights, model parameters. Then you will need to choose a learning rate scheduler like cosine annealing or one cycle or this custom one from the lectures. It will be similar to this. So scheduler equal torch dot optim dot lr scheduler dot, for example, cosine annealing. We say optimizer and like T max, so maximum number of iterations, like also 200, something like this. And we can also, yeah, and we should also say here the scheduler.step if you want to use a learning rate scheduler. So we recommend to use Adam or AddOW for optimization, cosine annealing one cycle or custom one for scheduler. Then after you define this optimizer scheduler, your model and data set, all you have to do is to iterate over your data in batches using your data loader. For each object, you calculate your model output, you calculate your loss, you call loss.backward, you calculate, you update your weights using optimizer.step, you update your learning rate using scheduler.step, And then you should not forget to zero your gradients to avoid this accumulation problem, and you call optimizer.zeroGrad. Then you do the same thing for many iterations, and voila, you are the winner, you trained your model. Another thing is to evaluate the quality of your model, but we'll talk about this on Wednesday. Yeah, it's pizza. One second. Yeah. And one extra advice. So if you are trying to reproduce a paper about deep learning, it is a good thing to exactly use the same setup as these researchers did, because maybe with their setup, the solution is working, but with some other hyperparameters, some other optimizer, it is not working. One thing is that if you look at the older papers or some papers from people who are not like very good in optimization or maybe don't care, they can use some relatively bad optimizers like RMS prop, which now nobody uses. So it's on the one side, it is better to use RMS prop to reproduce the results, but most likely you will achieve better performance if you use Adam or AdamW, and it won't hurt. So one advice is exactly copy paste the setup from the paper if you want to reproduce it or get the same results, but also carefully think about what you are choosing. Like if something is probably outdated or they use like constant learning rate, try cosine annealing, try one cycle, and you'll probably achieve the same performance or maybe a better one. Any questions? No, any questions on Zoom? No. Then for today, that's all. People who are on site will have pizza in 2-3 minutes. People on Zoom, sorry, you won't have pizza. Come on site.